we're very happy to have Zach Chase from Oxford, who is going to dispel a mystery of the primes for us. So welcome, Zach. Take it away.
Thank you. You can hear me, right? Right. Okay.
Yeah.
Right. Okay. Yeah, so I don't know about dispelling a mystery of the primes, but something about the primes maybe. Okay, yeah, so this is about Gilbreath's conjecture, which is easiest to show with a picture. So the first row is the sequence of the primes. Everything will be infinite, but obviously for graphical reasons, I have to truncate. And to get to the next row, you take the absolute value of the difference of the two terms above. So the absolute value of 2 minus 3 is 1, 3 minus 5 is 2, 5 minus 7 is 2, 7 minus 11 is 4, etc. And then the third row, each number is the absolute value of the difference of the two numbers above it. So absolute value of 1 minus 2 is 1, 2 minus 2 is 0, 2 minus 4 is 2, etc. And then Gilbreath's conjecture, as with the red, is like if the first term of every sequence past the first is a 1. Yeah, okay. So in 1878, Proth first made the conjecture, but he did not conjecture it. He provided a proof, but that proof was wrong. And then in 1958, Gilbreath independently made the conjecture while supposedly doodling on a napkin. Yeah, the bottom left is Proth. The bottom right is Gilbreath, who's mainly a magician, who's known for inventing a shuffling algorithm. And he still does performances to this day, even during the pandemic. Okay, so an obvious question is whether Gilbreath's conjecture really has anything to do with the primes at all. So note that you can prove Gilbreath's conjecture is true by showing that zeros and twos form to the right of the leading one early on. So I mean, you can see that that's kind of the case here, and it's sufficient because if you only have zeros and twos, then those keep pushing down to only zeros and twos, and then the one keeps hitting against them, so it'll always be a 1. Okay, so let's see what's going on with these zeros and twos. So let's just drop the first term of each sequence, and then let's ignore the first row. I'll explain why in a second. So the first row is now just the gaps between consecutive primes, and then all these numbers are even, so let's just divide by 2 for ease. So you have some sequence like this, and then the question is whether it quickly becomes all zeros and ones, which seems to be the case with the primes. So an obvious question is whether any initial sequence of positive integers becomes zeros and ones after a few iterations. And the answer is obviously not, no matter what few means, because you can just have a bunch of small numbers and then take a really big one, and then that'll stay big. Okay, but what if the gaps, what if the initial row is small? And still, of course not, you can just take something. You can just take a sequence of all zeros and threes, and then that keeps pushing down to all zeros and threes. And the next question is okay, what if you exclude something stupid like that? Well, it's not that simple. You can have, there are non-trivial things that push down to only zeros and threes, such as that thing shown below. And then you can go to a row above that and go to a row above that, etc. And these inverse iterates quickly become really seemingly chaotic. So it's kind of hard to predict which initial sequences will push down to only zeros and threes, for example. Okay, but you might ask must.
Yeah. So by push down to zeros and threes, you mean that it is eventually only zeros and threes? Is that what you mean?
Yeah, so sorry, if I ever use annoyingly vague language, just tell me, because I don't realize it a lot of the time. Yes, so we're talking about initial sequences, and then if you do one iteration, that's pushing down. So that iterate to only zeros and threes at a certain point. Maybe the final thing is 0, and you might say, oh, that's iterating to only zeros and threes, but I'm just being a bit loose with my language right now. I just mean it's not the case that they only iterate to zeros and ones after a few iterations. And an example of when that doesn't happen is if after a few iterations, everything is a 0 or a 3. So thanks. If anyone wants to say anything, just say it. Okay, but a question is whether those inverse iterates must have really large elements, right? We already asked about what if the initial sequence has a bunch of small numbers. So maybe if you keep going up and up, to inverse iterates of this 4, 1, 4, 7 sequence. If you keep going higher and higher, then the numbers get really large. But no, you can have so if you look at this kind of example, here this bottom row is only zeros and threes, and if you look up at 8 inverse iterates, this initial sequence is like still small numbers, like it's 8, like yeah, it's the largest number is 6, and after 8 iterations, everything's just a 0 and a 3. So that's kind of where the difficulty lies. It's kind of hard to predict which initial sequences will be annoying and like iterate to only 0s and 3s rather than only 0s and 1s after a few iterations. Okay, so then the question, so maybe that initial sequence that was just shown is kind of rare. So the question is like, what if the gaps are small and random? Maybe like most initial sequences that are small will push down to only 0s and 1s after a few iterations. And this is what has been conjectured repeatedly over the years since Proth and Gilbreath made their conjecture. And Olitzko did some numerical verification of Gilbreath's conjecture up to like 10 to the 11. He provided some heuristics and suggested that like, instead of using the primes, he used a sequence with small and random gaps. And Montgomery and the lecture series, like 10 lectures on the interface between analytic number theory and harmonic analysis, also asked in the open problem section what gap or density properties of an initial sequence satisfies the conclusion of Gilbreath's conjecture. And because this is like a fun and elementary kind of problem, there's been various blogs and online forums made talking about it, but there's been no papers on the topic besides Olitzko's numerical verification. It is hard to say something specifically about Gilbreath's conjecture itself. Okay, so here's our basic model problem. You form an initial sequence of length m by choosing numbers, let's say from 0 to 100 uniformly at random. So these are like the small numbers independently. And then the question is whether after a few iterations, everything is a 0 or 1. Yeah, with high probability. And yeah, we're imagining m very large here. So like the number 100 is fixed and then m is getting very large. So the answer is most definitely yes. I mean, we'll go over a proof, but more convincingly, you can just go on your computer and code it and you'll see that it's like definitely true, especially if the number 100 is replaced by like 10 or something and m is like a million. Like you'll see just very quickly everything becomes 0s and 1s. But once again, it's by no means trivial because like there are these kind of weird initial sequences that become all 0s and 3s after a few iterations and thus not all 0s and 1s. Okay, so this is our main theorem. So for m large, for any c between 3 and log m, we're just talking about c equals 100. If you form an initial sequence of length m by choosing numbers from 0 to c minus 1 independently and uniformly at random, then with probability at least 1 minus little o of 1, after little o of m iterations of consecutive differencing, everything is 0 or 1. So in the paper, the little o of 1 term was, you can take it to be exponential in e to the minus 5th root log m. So exponential in e to the minus 5th root of log m. So exponential minus e to the 5th root of log m. So it's a very small exceptional thing. And o of m, little o of m, you could take to be e to the 5th root of log m. But yeah. And then, yeah.
So is this meant to be a random model for the gaps between the primes? Is that the point?
Yeah, this will answer your question, hopefully.
Okay, great.
So this was like an answer to the model problem, and that like the model problem of, yes, this model problem. So the main theorem is an answer to this model problem, and then once we have this answer to the model problem, you get what the title suggests, a random analog Gilbreath's conjecture. So you start off with like an increasing function upper bounded by log m. You could pretend it's 100 if you want. And this will represent the gaps. So you start off with 2 and 3, just for parity reasons, and then the gaps are twice something drawn from 0 to f of n minus 1. So you could pretend it's 100, like f of n is 100. Yeah, so the gaps are just random between 0 and 200, and they're even, just for parity reasons. So that models the primes, kind of. Then with probability 1, there is some m naught, so that for all m greater than m naught, after m iterations, the first term of the sequence is a 1. So you can't just get like the first term of every sequence besides the first is a 1, but after some point, it will always be a 1. And to get this from the model problem, it's just kind of the intuition we were talking about before, like how if 0s and 2s form quickly enough, then the first term will always be a 1 combined with Borel-Cantelli. But the most interesting thing is the model problem. So before I continue, I just wanted to say a quick word about the motivation for this because it seems kind of like just a silly problem, but I think it's a pretty basic problem especially like the model problem. And the fact that it's non-trivial is what makes it interesting to me, at least, because it probably means there's some interesting math going on, because I don't know, you would think this kind of thing would be trivial at first glance, but surprisingly isn't. Okay, so so let's talk about the proof of this theorem.
Sorry, can I ask about the model again?
Yeah,
So
no problem.
the average gap between primes is bigger than log, right?
Yes, yeah, I was going to talk about that then, yeah.
Okay, all right, sorry, I'm jumping in.
No problem, it's fine. I told myself a mental note to say that right now, but I forgot. If you really wanted random, you would have a c up to log n or something like that. Yes, thank you. Okay, so for the proof, the first observation is that the maximum can never increase. Like if you have a sequence and the largest number is 9, you're not just going to get a 10 all of a sudden because you're taking differences. But more than that, you can see that like the largest number goes away pretty quickly. So like here, like you have this block of just 0s and 9s that's of length 3. And if you do 3 iterations, there are no more 9s because these like diagonals just kill it off. So more generally, there won't be any more hundreds after L iterations, where L is the length of the longest 0-100 block. So here I use 9 instead of 100 for graphical ease, but like I was just saying for the previous slide, if like, and by block, I mean like a contiguous block, like a contiguous interval of indices. So if you have 0 9s here, and then just something less than a 9, not 0, it just kills off this 9. So in the initial sequence, if you like separate these 0-9 contiguous blocks into like disjoint blocks, and call the length of the longest one L, then after L iterations, there are no more 9s. And so this is how the proof of the theorem should go. So like with very high probability, there won't be a 0-100 block of length log squared m in the initial sequence. And just to remind you, we're doing the theorem, we're doing the model problem with like 100 as the largest thing. So this first thing is obviously true. The distribution over the initial sequence is just IID uniform from 0 to 100. So obviously there won't be like a block of length log squared m of only 0s and 100s. That's just very unlikely. So what that means is that after log squared m iterations, there won't be any more hundreds. And then at this point, we have to be rigorous about this, but you would think that there's no reason that there should be a very long 0.99 block. By long, I mean length log squared m. So it should be the same thing. Like with very high probability, there won't be a 0.99 block of length log squared m after the initial log squared m iterations. So then you do log squared m more iterations to get the largest number, now at most 98, et cetera, et cetera. So after like, I don't know, 100 log squared m iterations or something like that, everything should be 0 or 1. That's kind of how the proof should go. So yeah, all you have to disprove is that like after any number of iterations, there's a really long 0D block for each d greater than 2. So for example, like if m is like 100 trillion, after like 1,000 iterations, there won't be an insanely long block of only 0s and 43s. So like that's literally all you have to disprove. And that's what made this question interesting to me, because like, yeah, I mean, there's no reason they should exist. So like you definitely won't have like the uniform distribution after 1,000 iterations, because the numbers get smaller. And like we expect to end up with only 0s and 1s after a few iterations. But besides that, like you should, in your mind, you should pretend like the distribution of the sequence is like still pretty random in the intuitive sense of random, except the numbers are kind of smaller. So for that reason, like for that intuition, there's really no reason at all that there should be a long like 0.43 block or something like that. But the question is, how do we do this? Okay, so it's actually easy to show that there won't be a long 0.42 block, but it's not easy to show there won't be a long 0.41 block. So let me explain why this is the case. So this consecutive differencing operation works well with reduction mod 2. So like you can reduce the initial sequence mod 2 and then take differences, or take differences and then reduce mod 2. It's the same thing. So what I mean by that, so this is not true with any other modulus. So for example, like you can have a number that's 1 mod 3 and another number that's 2 mod 3, and the absolute value of the difference, mod 3, depends on which number is bigger. So like the absolute value of 2 minus 1 is 1, which is 1 mod 3, whereas the absolute value of 2 minus 4 is 2 mod 3. Yeah, so, but with mod 2, like everything is fine. It's the information of which number is larger doesn't really matter. So due to this niceness mod 2, you can pretend that the sequence after any number of iterations is uniformly distributed. This is just like an easy induction argument, like the initial sequence is uniformly distributed mod 2, so after any number of iterations it is. And by uniformly distributed, I mean like IID, like 50, 50, 0, 1. So the probability that there's a long 042 block is incredibly small. And yeah, so 42 here is just any even number. So you can prove that, yeah, there won't be a long block of only like 0s, 42s, 06s, or whatever. Yeah, but how do we disprove that there's like a long 07 block, let's say? Okay, so the obvious question is like where a 07 block can come from. Well, it can come from, okay, I don't literally mean itself, but it could come from a 07 block, like 07 blocks push down to 07 blocks, so a 07 block can come from a 07 block. But it could also come from a sequence living in multiples of 7. Like, I mean, this is an example. So yeah, these are just the same two examples. But it could also come from a different coset mod 7. So note it has to come from some coset mod 7, because when you go from one number to the next, you're just adding, subtracting 7, or keeping constant due to the 0. So it'll come from some coset mod 7. So it can either like keep coming from like stuff 0 mod 7, or it can come from a different coset. And in this different coset, there won't be any zeros. So it suffices to show that after any number of iterations, it's very unlikely that a long block has no zeros. So let me just explain the logic again. So like if you do have a long block of 07s, you look like right above it, like where could that have come from? It can either come from multiples of 7 or a different coset mod 7. If it comes from a different coset mod 7, then like that long block will have no zeros, which is bad. If it comes from multiples of 7, you look above that. So it could keep coming from multiples of 7 all the way to the initial sequence. But we know that is very unlikely because you won't have a long block in the initial sequence of only multiples of 7, because we know the distribution of the initial sequence is just like IID uniform over 0, 100. So there won't be a long block of only multiples of 7 in the initial sequence, which means that at some point, like if you keep going up, you won't have multiples of 7 anymore. You'll have a different coset, and that like a block of stuff like 3 mod 7, let's say, and that block will have no zeros. So yeah, so that's why this last bullet is true. It's suffice to show that after any number of iterations, it's very unlikely that a long block has no zeros. Okay, that's this last bullet. And to do this, it suffices to show that after any number of iterations, for any particular index, the probability it's 0 is at least 1 over 1,000. And to demonstrate why this is the case, just a picture. So here we've done 2 iterations, and let's think about like whether this block on the bottom. So consider, like, imagine the sequence is much larger. We're just taking a chunk of it here, and let's look at for there to be no zeros in this block, there has to, like, this blue bullet has to not be 0, this red bullet has to not be 0, this green bullet has to not be 0, and this purple bullet has to not be 0. But the point is, like, you kind of have independence. So like this blue number right here, it's only influenced by these 3 blue numbers up here. This red number is only influenced by these 3 red numbers. This green number is influenced by these 3 green numbers, etc. The picture kind of gets messed up right here. But so the point is that for this block to have no zeros, you have to have like 4 independent events of not having 0. Like this guy has to be not 0, this not be 0, this not be 0, and this not be 0, which is independent. So like that's probably like 999 over 1,000 to the 4th. And in general, if you've done I iterations, then the probability that there's a block of length log squared m without a 0 is at most 999 over 1,000 to the log squared m over I plus 1. So yeah, so the point is, if you didn't follow that, here's a good checkpoint. If you got lost, like just all we have to show now is that for any I, if a1 through ai plus I are chosen uniformly at random from 0 to 100 independently, then the probability to ultimately iterate to 0 is at least 1 over 1,000. So now we just want a lower bound for, like, if you take I plus 1 numbers, what's the probability like the final number they iterate to is 0? So we just want to show it's at least 1,000. In reality, if I is large enough, we expect it to be a half, because we expect there to be only like 0s and 1s after a few iterations, and thus the final thing to be 0 or 1, but we just need to show 1 over 1,000. And okay, so you can use the reasoning we just talked about. So if there are never any long 0D blocks for any D greater than or equal to 2, then everything is 0 or 1 after not too many iterations. This is just what we just talked about before, right? Like if there's not a long 0 100 block, then you do a few iterations to get rid of all the hundreds. Then if there's not a long 099 block, you could do a few iterations to get rid of all the 9s, etc. And yes, so if there are never any long 0D blocks for any d greater than or 2, then everything is 0, 1 after not too many iterations. So the final thing you'll end up with is a 0 or 1, and then because of mod 2 considerations, like there will be a 1/2 chance of ending with 0. So what this means is that you can assume that there is, with high probability, a really long 0D block for some d greater than or equal to 2 and some number t less than I iterations. Does anyone have any questions at this point? I'm skimming through this too quickly, but yeah, so yeah, we literally just want to show that if you have I plus 1 numbers, the final thing they iterate to is a 0 with probability at least 1 over 1,000. Yeah, so and by the reasoning on the last side, we can assume that there is, with high probability, a really long 0D block for some d greater than or equal to 2 and some number t less than I iterations. And by the pigeonhole principle, there's some particular d greater than or equal to 2 and some particular t less than I, such that there's a decent probability that there's a long 0D block after t iterations. Whenever I say decent, I just mean like 1 over 1,000 or something like that, just some constant. This pigeonhole, it's not immediate that you end up with something like 1 over 1,000. Like I can be very large, so if you pigeonhole over t, you can have something go to 0, but I won't give the details, but you can do the pigeonholing efficiently so that, yeah, so okay, I'll come back to that later. So, okay, so what we showed is that if you take I plus 1 numbers, then after like a certain number of iterations, let's just say I over 2 for now, like, so with probability like 1 over 1,000, after I over 2 iterations, there will be a long block of only 0s and 43s in this row. That's kind of where we're at now. And by pigeonholing again, once again, you have to do it effectively. You can assume that the block starts at the first index. So with probability 1 over 1,000, if you take I plus 1 numbers from 0 to 100 uniformly at random, then this particular block in this row right here is only 0s and 43s with probability like 1 over 1,000. Okay, so then the main idea is to try to bootstrap this to get that with decent probability, the whole sequence after t iterations is only 0s and d's. So we know that like this thing is only 0s and d's. The question, like with probability 1 over 1,000, is it true that with probability like 1 over 100,000, this whole row is only 0s and d's? So that's the idea. And if we can do this, then we're done. Since then, like, if this whole row is 0s and d's, the final thing we iterate to is a 0 or a d, and thus it's 0 with decent probability since d will be odd and we have uniform distribution mod 2. The reason d is odd is because like if d is even, I mean, we just know that d can't be even because the probability that there's a really long block of only evens is very small because of uniform distribution mod 2. So the point is that like if we can show this whole row is only 0s and d's since d is odd, and because like you'll end up with as the final thing right there is 0 or d, with like if you multiply the probability by 1/2, like that's the probability you end up with 0, which is what we want. Okay, so what exactly do we know? Okay, so I'm just going to write down, like in English, what this means, that these guys are all 0 or d. So what this means is that like if A1 through AI is the initial sequence, the fact that this number is 0 or d means that A1 through AT plus 1, that like these guys, like the final thing they iterate to is a 0 or d. The fact that this number is green means that these numbers, A2 through AT plus 2, the final thing they iterate to is 0 or d, all the way through, and if this block is of length L, that means that like going up here, AL through AT plus L ultimately iterate to 0 or d. Okay, yes, so this is what we just said. So we know with decent probability, like 1 over 1,000, each of these tuples ultimately iterates to 0 or d. And just to remind you, that these numbers are just drawn uniformly at random from 0 to 100 independently. And what we want to say is that there's a decent probability that each of these tuples ultimately iterates to 0 or d. Yeah, so we have A1 through AI plus 1 drawn uniformly at random from 0 to 100 independently. We know that each of these first L tuples ultimately iterates to 0 or d with probably 1 over 1,000. We're asking whether with probably 1 over 100,000, let's say, like each of these tuples ultimately iterates to 0 or d. Okay, so what do we know about the tuples that ultimately iterate to 0 or d? By ultimately, I mean like the final thing they iterate to. So the issue is we know nothing about them. yeah, like if we know like which like t+1 numbers end up at 0 or d, then like everything will be easy. But the saving grace is that nothing might be good enough. So let me explain what I mean by this. So put a directed graph on t+1 tuples of numbers from 0 to 100 by connecting x1 through xt+1 to x2 through xt+1y. This is called a de Bruijn graph. And so these out edges correspond to like how the tuples go. So like here, the first tuple is a1 through at+1, the next one is a2 through at+2. So a2 through at+1, at+2. So like you'll have an out edge from this first tuple to the second tuple to the third tuple, etc. So that's like why we're looking at this kind of thing. And you color a tuple red if and only if it ultimately iterates to 0 or d. So, okay. So let's go back to what this is saying. So what this means, so if you think about it, this tuple right here is just a completely random tuple. Like a1 through at+1 are just random independent numbers. And then the second tuple is just a randomly chosen tuple from like out of the out neighbors of this tuple. So like out of all the neighbors in the de Bruijn graph, i.e. like all of the tuples that this has an out edge to, this is just a randomly chosen one, et cetera, et cetera. So sorry to keep going back and forth, but what this bullet means is that like if probably 1 over 1,000, if we choose a random starting point and then keep going along the out edges uniformly, all of the tuples you get are 0 or d. So if you color a tuple red, if and only if it ultimately iterates to 0 or d, that thing we were just looking at means that a random walk with uniformly chosen starting point of length L hits only red vertices with probably like 1 over 1,000. And then what we want to say is that like with probability 1 over 100,000, each of these tuples ultimately iterates to 0 or d. And what that means is it then true that a random walk of length L prime greater than L hits only red vertices, probably like 1 over 100,000. So just to recap, like with probability 1 over 1,000, a random walk of length L hits only red vertices. And we want to know, is it true that with probability like 1 over 100,000, a random walk of greater length hits only red vertices? Yes, so just repeating the question here. So this is a general question you can ask about like arbitrary colorings of the de Bruijn graph, and we kind of have to ask for arbitrary colorings because we don't really know what the colorings would be like, but our particular coloring would be like, but we could also ask it for general graphs. So if you got lost, here's another, we're just asking a very general question about random walks on graphs. So in general, no, you can't like bootstrap like a random walk of larger length hitting only red vertices. So consider this graph. It's the first half of the vertices are red, the second half are black. So if you take L to be the size of V over 4, then like with probability 1/4, a random walk of length L would be only red vertices. Here, a random walk and a walk are the same because there's only like one out edge. Yeah, so if you start in the first 1/4 of the vertices, then like, and you do a walk of length the size of V over 4, all the vertices will be red. So that's probably 1/4, random walk of length L will hit only red vertices. But if you take L prime to be like all the vertices, then the probability that a random walk of length L prime hits only red vertices is 0 because like you'll hit a black vertex. So you can't just, yeah, like arbitrarily bootstrap. And you can find these kind of examples in the de Bruijn graph, like colorings that, yeah, that fail. So that kind of seems bad. But you can note that in the example above, there is a decent probability of a random walk of length 2/5 times the size of V hitting only red vertices. So like if you start in the first 1/10 of the vertices and you do a walk of length 2/5 times the size of V, you will hit only red vertices. So you can't go from the size of V over 4 to the size of V, but you can go from the size of V over 4 to 2/5 times the size of V. And it turns out that a small extension is always possible. Yeah, okay, so here's the claim. So let G be a regular directed graph. Suppose that the set of vertices is red-blue colored such that the probability that a simple random walk of length L consists entirely of red vertices is at least C. So then a simple random walk of length 1 plus 1/10 C squared L consists entirely of red vertices is at least 1/10 C squared. So like we had like length L with probability C, we can bootstrap that to length 1 plus 1/10 C squared L with probability at least 1/10 C squared.
So
And
by a
note,
random
yeah,
simple walk, you mean you take a random starting point and you
yes,
make
yes,
random decisions at every point?
yes, thank you. Yeah, I forgot to say it. Yeah. Yeah, so yeah, the starting point is always chosen uniformly at random. If you don't choose the starting point uniformly, like if it's true that like if you start at any vertex and do a random walk, then this like kind of bootstrapping lemma is obvious, because then you could just like do a random walk of length L and then do a further additional walk starting from that endpoint of 1/10 c squared L. But yeah, so yes, sorry, thank you. When I say a random walk, I mean a uniformly chosen starting point. So yes. Um, And if you iterate this lemma, you get a summable geometric series of length increases. So like you start off with length L, probability C, and then you get a length increase of 1/10 c squared L, but the probability drops down to 1/10 c squared. So if you iterate this, you'll get a further length increase of like order c to the fourth, and the probability drops down to c to the fourth, etc. And if you add all these up, like the length increase is only of order c squared. So this doesn't contradict the example in the previous slide, right? This example showed that you can't increase the length from the size of V over 4 to the size of V, right? Because the probability a random walk of length L hitting only red vertices is 1/4, but for L prime it was 0. So yeah, you can only get a small length increase, and that's consistent with this lemma because, yeah. And I won't give the details, but this lemma is actually good enough to finish off the problem. You can, so if you followed what I was saying previously, you can actually take these green numbers. You can actually assume that like the first 99% of this row is only zeros and Ds. So that like when you do apply this bootstrap lemma, that's enough of a length increase to get the whole row. So I won't give the details, but like everything barely works out. Like you're actually, like even though this only gives you a small length increase, it's actually enough to finish off the problem.
I'm confused. So if L is just the length of the longest path consisting only of red vertices, what is this saying?
So if L is the length of the longest path,
If L is just the length of the longest path, then there is
yes,
some
so
probability.
yeah, so that probability will be very small. So I think I can encapsulate your question in this example. So like, I think what you're saying is like, let's take L to be the size of V over 2 and L prime to be the size of V over 2 plus 1, right? Then a random walk of length L prime hitting only red vertices is 0. But the probability of a random walk of length L hitting only red vertices is 1 over the size of V. Yeah, so the issue with that is the probability is too small there. Like we've always been talking about like constant probabilities. Yeah, so when I say decent probability, I forgot to mention this. By decent, yeah, I mean like a fixed number where the size of V goes to infinity. So to answer your question technically, like in the paper, if you look on archive, there's a floor function here. So if C is like 1 over the size of V, this will be an insanely small thing, and then this is just equal to L. Yeah. Yeah, obviously, like this number right here is not an integer. So yeah, you add the floor function is what's there, and that's why the 1/10 pop out. But yes, so you do need like when you apply this, you want like an actual constant probability. Yeah, and this lemma is like the conclusion is completely independent of the number of vertices, if you notice. Okay, so it seems like there's a lot of time left, but we can let's talk about the proof of this. So a key observation is that, like, let's say you have, here's a path of length L hitting only red vertices passing through V, but V is just some vertex, and here's another path of length L, a red path of length L passing through V. And if you have these two different paths, then you can form a longer path just by like going like this. So the point is like if you can find many V and many red paths of length L going through V at different times, then you can find many red paths of longer length. So like if it like hits V only like towards the end of the walk, and here it hits V towards the beginning of the walk, then like you can find a really long red walk, a red path. And then like by a Cauchy-Schwarz argument, which we're about to sketch, the fact that there are many red paths of length L allows us to find many such V. right? Like the assumption that a random walk of length L is likely to hit all red vertices is just the same thing as saying there are many red paths of length L. So this is kind of the idea of the proof. So it's not too technical. So if you can define weights W1 through WL on V by the jth weight at a vertex V is just the probability that a random walk of length L is all red, given that the jth step of the random walk is V. So by the assumption we have, and the fact that the graph is regular, which is necessary, each total weight, so for any weight, its total mass is at least C times the size of V. So if you, there's a common fact that if you have you have a set, you have a bunch of subsets of it of size C, of density C. Then if you have enough of them, there's 2 of them with intersection at least C squared. So the general fact is that if you have 1 over C squared subsets of a set of density C, then there's 2 of them that have intersection of density at least C squared. And the way that you prove that is by Cauchy-Schwarz. So that's a pretty general fact. It's used in ergodic theory a lot. But it's just a set thing about sets that you can prove by Cauchy-Schwarz. So it's a half a page argument, but if you do that, you get that 2 of these weights have to have a large common mass, a large intersection. I'll say why. So you do have 1 over C squared of them, and I'll say why I separated them in a second. But so this is true because you have 1 over C squared of them, and each of them has density at least C. And then the reason why you separated is by this picture on the previous slide. So what this means is that the fact that they have a common weight here means that you have many vertices V such that you have walks going hitting V at different times. So this one hits V at the J C squared L step, and this one hits it at the J prime C squared L step. Don't worry about the exact choices so much. The point is that these are separated numbers. C squared L, 2C squared L, etc. are separated numbers. So yeah, so the point is you do get a picture like this. Yeah, so by the picture on the previous slide, this gives a length increase of J prime minus J C squared L, which is at least C squared L, which is what you wanted. So yeah, so it's mostly just a Cauchy-Schwarz argument. Okay, so that's the end of the proof of the theorem. Are there any questions about anything before I go on a bit more? Okay. Okay, yeah, so a question after all of this is whether progress has been made on Gilbreath's conjecture. I would say no. I might actually say negative progress has been made. So the issue is that to prove Gilbreath's conjecture, you need to dispel that these kind of initial sequences are the gaps between the primes. Well, so it would be twice of this initial, if you multiply each of these numbers by 2, that's the gap between the primes. Because just to remind you, if you multiply all these by 2, this is the part of the sequences that come after the leading one, the supposed leading one. So if you end up with something like this will be all 0s and 6s. And if you did have a leading one, that will hit against the 6s and change to 5. So the point is that Gilbreath's conjecture is pretty much equivalent to ending up with only 0s, so to iterating to only 0s and 1s quickly. So okay, the point is that if these are if these are 1/2 the gaps between the primes, then you're in trouble. And you need a structural characterization. I think you need a structural characterization of these kind of initial sequences to prove Gilbreath's conjecture. And if you do find a structural characterization of these initial sequences, then all the work we just talked about becomes absolutely trivial. So what this work shows is that these sequences are very rare, but that doesn't help you when you're talking about a particular thing like the primes. The reason I say negative progress is this work kind of reinforces the idea that finding a structural characterization for these initial sequences is hard. So, okay. Yeah. Okay, so now for open problems. So I'd be really happy if someone can make progress in either of these, because I think they're very basic questions, but they're surprisingly hard. Oh, I wanted to say one other quick thing. It does seem like something like this is definitely necessary. I tried a while and asked some other people if there's a proof of the main theorem without using something like this, and it really doesn't seem like there is. So I feel like there could be something interesting going on here. It is pretty bizarre how like this argument, how this thing comes into play and actually is sufficient, but it does seem like you need something like this. So I don't know, I think there could be something interesting to all this. Okay, so the distribution of our initial sequence had three properties. The first is that it was uniformly distributed over 0 to 100. The second is that it's, well, the second kind of incorporates the first. Like we used, like each distribution was the same, i.e. like 0 to 100, and like we had independence. Okay, so the proof was sturdy in that one can use any reasonable distribution instead of the uniform distribution. So like maybe, like, I mean, so, yeah, instead of like exactly uniform, like, I don't know, maybe like probably 1 over 101, like 102, you choose 0, with probably like 1 over 3, you choose 1, etc. And you do need a reasonability assumption. Like if you always just choose 0 or 3, then you're screwed. But as long as you have something reasonable, the proof will work. The way that you adapt the proof is instead of looking at the De Bruijn graph, you add many duplicate vertices so that the random walk that you get on that graph models this different distribution. Okay, but the proof is not sturdy in that a common distribution is really needed. So, so this gives us our first model problem, or our first open problem. So form an initial sequence of length m by choosing the first number uniformly at random from 0 to 48, the second from 0 to 17, the third from 0 to 74, let's say. Like you just choose these numbers arbitrarily, but I insist that they're all less than 100. So like you could choose the first number from 0 to 48, the second from 0 to 17, the third from 0 to 74, the fourth from like 0 to 13, the fifth from 0 to 99, etc. With the choices independent. And the question is like, is it true that with high probability, after not too many iterations, everything is a 0 or a 1? Yeah, the proof just breaks down because you do need translation variance and everything to do this whole random walk argument. Yeah, so I mean, I think this is a very basic question. You can define high probability and not too many iterations however you like, as long as it's reasonable. Yeah, so I think this is interesting. Okay, the second open problem. So, okay, so we showed that for C anywhere from 1 to log m, we talked about C equals 100. But yeah, the proof allows you to go up to log m. If you have m spots and put numbers down uniformly at random from 0 to C independently, then with high probability after not too many iterations, everything is a 0 or a 1. Yeah, so that's what we showed. So an obvious question is how high you can take C. So like what Sean was getting at before, if you want to model the primes, you want to take C up to log m. Okay, and the guess is that C equals m is the limit. So if C is little o of m, then with probability 1 minus little o of 1, after m over 2 iterations, everything is 0 or 1. This is a guess. Yeah, so the probability cutoff, you can just say 1 minus little of 1, and the number of iterations, like you can just take it to the m over 2 if you want. And then if C goes to infinity with m, like C is m log m, then with probability 1 minus little of 1, after m over 2 iterations, not everything is 0 or 1. So not just the negation of the first bullet, but the opposite. Like with probability little o of 1, after m over 2 iterations, everything is a 0 or 1. Yeah, so I guess like, I mean, I think if you're a bit smarter with the proof than I was, you can get C to be log m over log m. But getting C to be log m or log squared m or even like root m or something, I think that's, yeah, I have no idea how to do it. In terms of the upper bound, I proved the second bullet if C is 2 to the m squared, but I didn't work on it too much. I think the lower bound's more interesting, but yeah, the upper bound thing. I don't know, there might be a trivial proof of that 2 to the m is an upper bound, but I have 2 to the m squared, but yeah. Also a fun open problem is whether trace reconstruction can be done in polynomially many traces, but that's separate. Okay, thank you.